Hello, testing.
Hi, Professor, can you hear me?
Yes, I can hear you. Thank you. Good evening. Welcome to Lesson 8, Calculus on a Saturday. So I'll start with answering a few questions and then we'll continue with applications of limits and continuity. So a question from the WeChat group: why do we have 0 less than the absolute value of x minus x0 in the limit definition? So we discussed this a bit, but let me state again the answer. It makes the definition more useful. So let me give a simple example. The reason is that it makes the limit exist in cases where we expect it. So, for example, if I take a function x which is 0, except at x equals 0 where it's 1. Okay. So the function is 0 except at x equals 0 where it's 1. Like that. So we expect the limits of this function to be 0, because as x approaches 0, the value is always 0. So this is true in the definition given. But if we remove the greater than 0, oh, sorry, yes. First, remove greater than 0, limit does not exist. Okay, so, and if that last bit is not clear, please go back and check it with the definition if you're worried about this issue. Okay. So a related question. Why do we have to be careful about the definition of a limit? Isn't it just obvious when the limit exists or not? And the reason we have to be careful is because functions can be very strange. So this was mentioned last time when one of you mentioned the Cantor set. So that's one example that gives a very strange function, but let me just give a simpler one, which is from the book. So, end of chapter 2, exercise 17. If I put fx is just x, if x is rational, and 0 otherwise, then this is continuous at 0, but it's not continuous anywhere else. So we can't tell this from the graph because the graph is impossible to draw. So if you just think about that function a little bit, you'll soon see that you're never going to be able to draw a graph of it. But it's still a function, we can ask whether it's continuous or not. So we need an algebraic, well, we need a precise definition. Okay, and we'll see more and more how this precise definition has good consequences. Okay, so let's go back to so continuous extension. And last time, just one more example of that. So if we take the function f of x given by x squared plus x minus 6 over x squared minus 4. So notice that we can factorize x plus 2, x minus 2, and what do we get? X plus 3, x minus 2. We can factorize like that. And so that is equal to x plus 3 over x plus 2. Obviously there we're using that x is not equal to 2. So domain of f is the real numbers with minus 2 and 2 removed. But using above calculation can extend continuously. Can extend to fx x plus 3 over x plus 2. So this now has domain R with minus 2 removed. Because if x is minus 2, then x plus 2 is 0. Okay, so let's draw the graph to explain what's going on. So that x plus 3 over x plus 2 is equal to 1 plus 1 over x plus 2. So that lets us draw the graph by shifting the graph for 1 over x. So what do I get? So I think I'm actually just going to draw a piece of the graph. So if this is 2 and this is minus 2, and then this is 1, then the graph is given by taking the usual graph for 1 over x and shifting it. Let's draw that in. Something like that. So we can see why minus 2 is not in the domain, because there, well, for the same reason that 0 is not in the domain of 1 over x. I'm going to draw in the y-intercept here, that's 3 over 2. But if I make this the graph of fx, then also 2 is not in the domain because of the way we defined fx. So this point is also missing. So when x equals 2, f of x is close to 5 over 4. But this capital Fx that we've defined that actually equals 5 over 4 at this point. So this is now 5 over 4. Okay, so we see the difference in the two domains. Okay, so the first important theorem that uses continuity is called the intermediate value theorem. And this theorem is saying something that is very obvious intuitively for certain sorts of graphs. But continuity is needed to make this true. So why is continuity useful? This is one of the most important answers, this theorem. If y equals f of x is continuous on a closed interval AB, then it takes every value between FA and FB. So let me say that out of the way. If I choose y0 in the closed interval FA and FB, then there exists some C in the domain AB such that the value at C is y0. Okay, so in a picture, with a continuous graph, this is quite clear. So that's my interval a to b. There's going to be some c in there. And say this is the value at a, and this is the value at b, and this is the y naught I want to find as a value. So we're starting there and ending up there, and we can go any way we like between the two, but the theorem says that if you choose any y0, then there will be a c such that the value at c is y0. So what's the idea here? To get from FA to FB, must pass every value in between. So if you think of the horizontal axis as time and the vertical axis as position, if you're going from one place to another place, even if you go backwards at the beginning, you can't get to the other place unless you pass every point in between. So, but the important point if the function f is not continuous, then the conclusion of the theorem may be false. So I'll give an example in just a moment. I'm just going to come and check back, see if there are any questions. So, question from Mu. Yes, so the limit does not exist if we remove less than 0 or greater than 0. So you've written less than 0, it's actually greater than 0. So the limit does not exist. So I think you should look at the definition until that is obvious. So it needs some thought, but I think you have to think about that on your own. So must the value of y0 always be in between fa and fb? Yes. I see. So the point is that if we take a y0 between fa and fb, then we can find a c such that the value at c is y0. If we take a y0 which is less than fa, then there may not be a c such that the value at c is y0. And that's because the function does not have to go like it's gone in this graph. The function could be linear between fa and fb. And if I then chose y0 less than fa, then there would not exist a c like in the theorem. Is that clear? Okay. So let me show an example of why this theorem needs continuity. So example from the book. So if I take a function f like this, there does not exist any c in the domain, which is 1 to 4, such that if y0 is 2.5, for instance, fx equals y0. Sorry, said that wrong. I meant y0 equals fc. Okay. So for this function, the theorem is not true, but that's because this function is not continuous. So this theorem is useful for proving that roots exist. So for example, fx equals x cubed minus x minus 1. So what are roots? Roots are solutions of fx equals 0. And for a cubic equation, these are hard to find. For a quadratic equation, you could do this, but for a cubic, it may be harder. So, I have a graph of this, yes. So let's note that from this graph, we see there seems to be a root between 1 and 1.5. But now we can prove this. So f of 1 is 1 cubed minus 1 minus 1 equals minus 1. And f of 3 over 2 is 3 cubed over 2 cubed minus 3 over 2 minus 1. And let's put that in one fraction. We get 27 over 8 minus 12 over 8 minus 8 over 8. And that gives us 7 over 8. And so we can now prove that there's a root between 1 and 3 over 2. How do we do that? So f is continuous on R because it's a polynomial. So f is continuous on a smaller domain, for instance, 1 to 3 over 2. This. Proving. Okay. So using the theorem, where we set y0 to be 0, and I'm using that interval because f maps this a and b to these values here. And therefore the theorem says that we have C in the interval AB such that SC equals 0. And in other words, C is a root of x cubed minus x minus 1. The remark can prove a root exists without even calculating it. So we already see how these definitions of continuity and this theorem are powerful. Okay, so now I'm going to go back to discuss more notions of limits. These are called limits at infinity. So I'll explain what that means. So note here the order in the syllabus, which is on Learn, is different to Thomas. 11th edition here. So in Thomas, we're now back to section 2.4 from section 2.6. So a note, we're going to be using the symbol infinity here. So just a note, discussed before, that infinity is not a real number. I think we know this. But it's a useful symbol to describe functions for large x. Okay, so let's give an example. So again, I'm going to say what I want the limit to be, and then I'll give a definition that matches with that. So let's take the function y equals 1 over x. So in this case, I want to say that the limit as x goes to infinity of fx is 0. So what am I trying to say there? Just that as x gets large, then fx gets very small, and fx can be as small as I like, so I say the limit is 0. And in the same way, I want to say the limit as x goes to minus infinity of fx is 0 for the same reason. So what definition gives me things like this? Well, it's a variation of the limit definition from last time. So we write that the limit of fx as x goes to infinity is L if for all epsilon greater than 0, there exists M such that if x is greater than m, then fx is close to L. So you should think of this as saying that however close I want the values to be to L, I can choose some m. So think of m as a big positive number, such that if I'm bigger than that number, then the values are forced to be close to L. Let me write an example for m here. So say at this m, say it's 2, the values are forced to be within half of 0. If I want them to be within a quarter of 0, I could choose 4 and so on. Okay. So we also wanted the limit as x goes to minus infinity. So I'm going to write that in the same definition, just to show how you change it to get the minus infinity definition. Well, for x goes to minus infinity, let's use a different letter. Let's say there exists n such that if x is less than n, then the value is close to L by epsilon. And in this case, we say the limit of fx as x approaches infinity or minus. Okay, so now we'll talk about how to calculate these limits. First, let me go back, see if there are questions. Create some questions. Okay, so a further question from Moo. Yes, so maybe so x minus x0 can be 0 if x and x0 are equal. But in the definition of the limit, we ask for it to be greater than 0. Yeah, and so Zhang, yes, the theorem applies to all continuous functions, not just linear equations, but I think you understood. Okay. So as before, with usual limits, we have the limits of the constant function. So here we mean, so the limit as x goes to plus or minus infinity, the constant function is of course that constant, the graph is just horizontal. And also, we can prove that the limits of 1 over x as x approaches infinity or negative infinity and 0. And like before, we can build up more knowledge about limits using limit laws. So the limit laws for sums, products, etc. They work. And the sandwich and comparison theorems also work. So let's give a few examples. The limit of 5 plus 1 over x as x goes to positive infinity. Well, that's a sum, so it's the limit of the sums. The limit of the constant is the constant 5, and the limit of 1 over x is 2. So we get 5, and what about the limit as x approaches negative infinity of 1 over x squared? Well, 1 over x squared is the square of 1 over x. So the limit law gives us that it's the square of the limit of 1 over x. And we said that's 0. Okay, so a more challenging example is given by rational functions. So here there's a trick. We divide by highest power in the denominator. So let me show you what I mean. If I want to find the limit as x goes to infinity, 5x squared plus 8x minus 3 over 3x squared plus 2, then the first step is to divide by x squared. It's the highest power in the denominator. So divide on top and bottom. And then I get, this looks like a crazy thing to do, but there's a good reason for it. You get this. And then I can use the limit laws to calculate this limit. So it's a quotient. So the limit is the quotient of the limits. 5 is its own limit. 1 over x has limit 0. Minus 1 over x squared has limit 0 as well. And on the bottom, we have 3 plus 0, so the answer is 5 over 3. Okay, let's take a break. Okay, so message to student Mu. I put in the notes some explanation of why, if we remove greater than 0 in the limit definition, the limit does not exist in this case. And similarly, if we remove the greater than 0 from the limit definition, the limit does not exist in many cases where we would want it to exist. Okay. So I know this is a little bit complicated and subtle, but if you just think about it and read over the examples again, I hope it will become clearer. It just takes a bit of time. Okay, so back to this calculation. So I need to justify one point. You notice I divided by 0 here. And why is that okay? Because limit only depends on values of function for large x. So that's just from the definition. It's in the same way that the limit as x approaches a point C only depends on the values of the function near C. So we could shrink domain to, for instance, 100 infinity. And we'd still get the same result for the limit, but of course then x could not be 0, so we can do the calculation. Okay, so some terminology. Which helps us to draw graphs also. So the line y equals b is an asymptote of the graph y equals fx if one of the following is true. If the limit as x goes to infinity of fx is b, or the limit as x goes to minus infinity of fx is b. So This is true in the example above. And a simpler example, y equals 1 over x has asymptote y equals 0. So again, drawing this is the asymptote, and the graph is approaching that line as x gets bigger or x gets smaller. X gets bigger in the positive sense, or x gets bigger in the negative sense. So let me draw that in. So graph approaches asymptote as x goes to minus infinity, or x goes to positive infinity. So the sandwich theorem is useful to calculate these sorts of infinite limits. Let's take y equals 2 plus sine x over x. Now we know that the absolute value of sine x is at most 1. So if x is not 0, then I can consider the absolute value of sine x over x, and this is going to be less than or equal to the absolute value of 1 over x. And we have the limit as x goes to plus or minus infinity of the absolute value of 1 over x is 0. So depending on the sign, this is either 1 over x or it's minus 1 over x. So in either case, we get that limit 0. So the sandwich theorem gives that the limit as x goes to plus infinity or minus infinity of sine x over x is 0. Actually, so I'd rather do this calculation in a different way. I'm going to change this slightly. So I don't need all these absolute values. There's a more direct way to do this. So the absolute value is less than or equal to 1. So it's between -1 and 1. And therefore, sine x over x is between 1 over x and -1 over x. And the limit of 1 over x equals 0. But also the limit of -1 over x equals 0. Write that in. So the sandwich theorem gives this. And then a limit law gives the limit of the function we want. It's just 2 plus 0, which is 2. So y equals 2 is an asymptote. So it looks a bit different to the 1 over x asymptote. It looks like this, the red line here. But we can see that the function approaches this as x goes to infinity or minus infinity. Okay, a question. Okay, thanks, student Moo, great. Oh yes, good point. Okay. So a message in the chat correcting me. So what I said was true for x greater than 0, but not true for x less than 0. Can you see why? Because for x less than 0, -1 over x is positive and 1 over x is negative. 1 over x is negative. -1 over x is positive, and sine x is between them. Okay, thanks very much for that. Okay, so now another sort of infinite limit. Which will give us another sort of asymptote. Okay, so I've drawn this graph many times this class, but in each case for a slightly different reason. So let's draw it again. Fx equals 1 over x. So we've studied the horizontal asymptote. But now I want to understand also the vertical asymptote. So this vertical line where the graph approaches. As x goes to 0 and the values get very large, the graph approaches this vertical line. So that's also going to be a vertical asymptote. So in this situation, we write limits like this. So the limit as x approaches 0 from the right of fx equals infinity. And the limit as x approaches 0 from the left equals minus infinity. So you can see from the graph what we mean by this. We mean that as x approaches 0 from the left, the value becomes very negative. But we have to be careful. We don't mean that the limit equals a number, because infinity is not a number. So let me write a note to make that very clear. So the symbol infinity is not a number. Okay, so maybe we've accepted that. But in this case, there's something even a little bit stranger. That writing like this does not mean that the limit exists. Because remember, we discussed last time that limits like this do not exist. But this writing means something quite particular. So we'll give a definition in a moment. But when we write this, we just mean that values of fx become as large as we like either in the positive or negative sense. As x approaches. And again, we mean from the left or the right. Okay. So let's give another example. If I now take 1 over x squared, and I look at the function close to 0, then I want to write that the limit as x approaches 0 from the right of f of x is positive infinity. That's also true as the limit approaches from the left. It's an even function. So it would make sense. Remember, if the limit from the left exists and the limit from the right exists and they're equal, then if it's an ordinary limit, that means that the limit exists. So we want to write the same thing for these infinite limits. We want to write the limit as x goes to 0, f(x) equals infinity. Okay, so what's the right definition to give? That's another variation on the limit definition. So we write the limit of f(x) is infinity as x goes to 0 if for all b greater than 0, there exists delta such that if x is close to x0, so I'm taking the limit as x goes to x0. If x is close to x0, but not equal to x0, this is the thing we were talking about at the beginning, it's still there, then f(x) is greater than b. So the idea here is that for any b, however big that b is, I can make x close enough to x0 so that the value is forced to be bigger than b. And then what do I write for minus infinity? Well, it's very similar. So if the limit is minus infinity, then for any positive b, I want f(x) to be less than minus b. So think of b as a big positive number. So I want f(x) to be less than minus b, which is a big negative number. So we say that f(x) approaches infinity. or minus infinity. And we have this example that the limit of 1 over x squared as x goes to 0 is infinity. Not 8, but infinity. And if you want to prove this in the above definition, we need to find for each b greater than 0 a delta such that that's true. And we use delta is 1 over square root of b. That's the trick. So you use that delta, or any smaller delta also works. So note, we also wanted to make a definition for when x approaches x0 from the left or the right. So like this. So this is x goes to x0 from the right. And we do this by modifying this bit here in the same way as before. So we just have the same inequality there as we did for the other one-sided limits. Okay, and another remark. So in this definition, it also makes sense to take this 0 less than x minus x0 in definition. And why is that? Because if that absolute value is equal to 0, then x equals x0, which in this case is 0, and function not defined. Okay, so we have this definition saying that the function approaches infinity as x goes to a particular x0. And we now have a definition of vertical asymptote. So a line x equals a the vertical asymptote of the graph y equals fx if the limit from the left of fx is plus or minus infinity, or the limit from the right is plus or minus infinity. Okay, so let's now calculate for an example we saw before. Let's find all the asymptotes of y equals x plus 3 over x plus 2. So notice y can be written as 1 plus 1 over x plus 2. And we can see that the domain is r but not minus 2. So let's calculate the limit as x goes to minus 2 from above of this. Well, by the limit law, it's 1 plus the limit of this. But 1 over x plus 2 is just a composition of functions. Add 2 and then do 1 over x. And we know the limit of 1 over x as x goes to 0 from above. So that gives us, mistake here. So we know this limit this is infinity, because we know that the limit of 1 over x as x goes to 0 from the right is infinity. Okay, so that tells us that x equals minus 2 is an asymptote. So that's the vertical asymptote. And let's also calculate the limit as x goes to infinity. Well, that's 1 plus the limit of 1 over x plus 2. So that's 1. So by what we said before, y equals 1 is an asymptote. And that matches up with the graph. Let's draw that. So it can be helpful to draw these asymptotes first. So we have y equals 1, and we have x equals minus 2. So we can use these to sketch our graph. And get something like this. So check. So the x-intercept, the y-intercept, we just calculate that by putting x equals 0. So the y-intercept is 3 over 2. And the x-intercept is minus 3. Okay, just come back to the check. So question from student 2690. Shouldn't this definition also apply to the questions above? So going back, so yes, this definition applies to the situation at the top that I'm showing now. So in this situation, as x approaches 0, the value fx will get as large as we like. And the definition shows us when exactly we can write that the limit equals infinity. But we have to be careful because we can write the limit equals infinity, but infinity is not a number, so that does not mean that the limit exists. Okay, and now I understand the question from Nat. Why is the definition for asymptote or instead of and? Well, let me give an example. So question, why or in the definition? So the definition was a line is a vertical asymptote if the limit from the left is infinity or minus infinity, or the limit from the right is plus infinity or minus infinity. Well, the answer is that might not be able to take limit from both sides. So for example, if I take function square root of x, then I could look at the function 1 over square root of x. And then this line is an asymptote because if I let this be fx, the limit as x goes to 0 from the right equals infinity. So the values of f approach infinity as x goes to 0 from the right. But we can't talk about the limit as x goes to 0 from the left, because domain of f is R plus. Okay, thanks for the question, Nat. Okay, so we have 1 more minute, and I think that's a good point to finish. Please enjoy the rest of your Saturday night. See you on Monday. So finishing a bit early, thank you.